Welcome to the Flight Readiness Review for Autonomous Aerial Vehicles at Virginia Tech. Over the next 20 minutes, we will provide you with a brief overview of our UAS and flight testing to demonstrate that the system is refined to a point where it can compete in the 2024 SUAS competition. Our team operates through a collective effort of 14 undergraduate students majoring in the fields of mechanical, electrical, computer, aerospace, and general engineering, as well as computer science. The team is divided into two sub-teams: Structures and Propulsion, and Autopilot and Electronics. The Structures and Propulsion subteam consists of 8 members, while the Autopilot and Electronics subteam holds 5 members, and the team's 14th and final member is the treasurer. Although all members play a critical team role, the competition team will consist of 3 operators. Finn Riley has been on AAV for 3 years, is the team lead, Autopilot and Electronics lead, and will be the ground control station operator at the flight line. Jonathan Ryerson has been on AAV for 2 years, is the Structures and Propulsion lead, and will be in charge of the payload systems at the flight line. Will Ponte has been on AAV for 1 year and will be the safety pilot at the flight line. Introducing Grey Goose, a custom quadcopter aircraft capable of fully autonomous air delivery of multiple water bottles using an onboard imaging system. Throughout system development, our team has emphasized the importance of testing, safety, and reliability to ensure that all components on Grey Goose are ready for flight. Requirements and acceptance criteria. Grey Goose was designed and developed for optimal completion of the package delivery mission synopsis given by the 2024 SUAS competition rules. To remain competitive at the 2024 SUAS competition, the team's previous system was upgraded in alignment with the more challenging payload delivery criteria and mission layout. Please pause the video to review the table on the screen that details each mission task, alongside the team and system requirements that align with such tasks. To achieve all the requirements set forth, the team knew that weight reduction and flight efficiency were key factors in the design process. Targeting a system capable of carrying multiple water bottles and traveling 15 miles at a minimum average mission speed of over 45 miles per hour, while ensuring that the ODLC and airdrop systems are rigorously tested to ensure reliability. System overview. Grey Goose is a custom-designed quadcopter capable of flying long distances while carrying multiple payloads. Grey Goose is capable of carrying 5 water bottles at a time, and the team is confident in its ability to perform well during the mission demonstration. Due to travel restrictions, the aircraft's total dimensions were limited to a maximum of 1,200 millimeters. Each component on the UAS was designed to be easily detachable for troubleshooting on the flight line. This modularity minimizes the amount of time spent repairing Grey Goose in the event of a crash, allowing for increased flight hours prior to competition. Imaging and ODLC design and testing. Grey Goose's imaging system consists of a GoPro Hero 7 Black that is connected to the HearLink air unit, providing real-time video feed to the ground control station at 4K 60 FPS. In order to ensure that the GoPro Hero 7 Black would be able to resolve objects of the size required by the competition, a DJI Mavic Air was flown at various altitudes to collect images. This allowed for the visualization of several object resolutions before the purchase and integration of the GoPro Hero 7 Black. Live streaming the video feed down to the ground operators removes the need for onboard image processing algorithms. Once the appropriate object has been localized, Grey Goose will then autonomously navigate to the point and conduct the appropriate delivery process. The team found that although this manual ODLC process requires an additional operator, it greatly reduces the probability of a failed airdrop attempt due to poor algorithm performance. To assess and improve the performance of Grey Goose's object detection system, numerous test flights were conducted in competition conditions with mock objects. This included practicing the manual imaging technique previously mentioned in order to become acquainted with Grey Goose's exact needs. By monitoring the image quality at several altitudes, the team found that hovering at approximately 80 feet resulted in the highest image quality resolution of approximately 2.5 centimeters per pixel. Airdrop design and testing. In order to complete the airdrop task, Grey Goose carries 5 onboard winch systems, each holding 1 8-ounce water bottle to be safely lowered to the target below. Unlike a fixed-wing aircraft, Grey Goose can deploy its held water bottles while hovering in place above a desired drop location, removing the need to determine the optimal drop time. To further minimize the effects of wind and drag, the bottles are always delivered from 80 feet above the ground. The delivery mechanism consists of a custom-designed winch and release system. The bottle is secured directly to the bottom of the craft by a servo-controlled release mechanism. The mechanism is designed to ensure that the bottle stays securely mounted to Grey Goose even if the servo fails. Grey Goose's onboard winch is composed of a spoked wheel that has been paired with a 60mm radius pulley and 80 feet of fishing line. The spoked wheel consists of 8 elongated arms that collide with a bar during rotation, slowing the rate of descent of the bottle. The resulting descent rate is approximately 5 feet per second, and the total drop time is approximately 15 seconds. The airdrop system has been tested in numerous flights on board Grey Goose. The results of 20 attempted deliveries show that the water bottle lands with an average accuracy of 3 feet from the target, with 90% of deliveries occurring within 5 feet. Independent of the delivery accuracy, the bottle survived in all tests, and ground personnel felt that no risks were posed during the bottle's descent. Communications design and testing. Through the use of HearLink air unit and the pilot controller system, Grey Goose is able to combine its telemetry, transmitter, and ground control functions into a single, compact device. The estimated range for the HearLink system is over 12 miles, with higher range values being reported by replacing the stock antennas with directional antennas. By operating at 2.4 GHz, the HearLink system is also capable of performing reliability during operations around structures or other obstructions. This range and throughput allows for a reliable pipeline of communication between all ground operators and Grey Goose, with data mirrored to a laptop running QGC for GCS support. This same setup was also used by our team during the 2023 SUAS competition, with no performance issues or link lossage. In terms of communication testing, the range of the HearLink system was tested up to 1 mile in order to assure steady communication throughout all phases of competition flight. This range was limited mostly due to the line of sight operational requirements necessitated by the FAA. With less than 5% packet loss and constant transmission, the HearLink system suffered no loss of communication throughout all phases of flight. Aircraft design and testing. The base airframe consists of 4 arms, 2 center plates, and 2 landing legs. In order to maximize strength and minimize weight, the airframe is composed primarily of carbon fiber, with aluminum reinforcements at high stress concentration areas. Grey Goose's electronics are contained in between the bottom and top carbon fiber center plates, with the exception of all components related to the payload system on board Grey Goose. At a takeoff weight of 11.2 kilograms, Grey Goose has a minimum thrust to weight ratio of 2.6 to 1, and is capable of traveling at a max horizontal speed of 45 knots. Please pause this video to review the aircraft metrics shown on screen. Before constructing the airframe, multiple static and dynamic loading simulations were conducted to verify structural integrity. Using Fusion 360, our team was able to quickly conduct multiple simulations and analyses that led to the finalized airframe design. Several carbon fiber plate thicknesses were tested in an attempt to minimize the airframe weight while maintaining a minimum FOS of 1.5 to 1. Fatigue stress was also calculated using an alternating von Mises approach with a fluctuating load from 0 to 8.75 kilograms. The max thrust applied onto a singular arm by the propulsion system. The propulsion system on Grey Goose was chosen based on its fulfillment of requirements set forth during the mission requirements analysis. In order to reach optimal efficiency, the propulsion system was designed using low kV motors paired with large propellers. The propulsion system is composed of T-Motor MN605S 170 kV motors, Alpha 60A 12S HVESCs, and MF2211 carbon fiber propellers. The aircraft is powered by 2 6S25AH LiHV batteries, wired in series to supply the aircraft with a 12S 50 volts power supply. This battery configuration enables an extended flight time and results in a theoretical range of 19 miles at a 45 mile per hour cruise speed, while ensuring 20% battery reserve. The aircraft was tested in several flights with both mock and actual payloads, since stabilizing the flight of a multi-rotor is tightly connected to the autopilot performance. Many of the initial flights were designed around tuning the autopilot performance. Once the autopilot stabilization was tuned, Grey Goose was flown for approximately 2 hours across more than 15 flights. No in-flight failures, crashes, pieces falling off of the aircraft were observed throughout the whole season of testing. Many of the base flight performance requirements regarding angle of climb and turning radius were achieved due to the multi-rotor nature of Grey Goose. Therefore, the team focused mainly on ensuring Grey Goose was capable of achieving the 15-mile flight distance when fully loaded. Competition-esque waypoint missions were to prove this capability, where Grey Goose was able to achieve over 19 miles of flight range while flying a square pattern where each lap represented 1 mile of distance. Upon landing, Grey Goose's battery level always remained above 20%, providing a good buffer for performance loss due to high winds or large altitude changes. All systems were further inspected following the flight to ensure that the components were not being stressed during flight. Autopilot design and testing. After comparing all commercial autopilot systems, our team observed that the Cube Orange was able to fulfill the autopilot requirements in addition to support for additional experimental crafts, internal heating, and triple sensor redundancy. Its open source nature also allows for external software manipulation and completion of tasks such as ODLC. Our team's past experience with the platform also lowers the risk of user error when integrating the platform into Grey Goose. In order to maintain precise and accurate location data, an external Here Pro GPS module is connected to the Cube Orange. This allows Grey Goose to perform reliable waypoint navigation with variable waypoint accuracy as high as 3 feet. In terms of autopilot software, Autocopter's open source nature, ability to communicate with the GCS, base obstacle avoidance features, and autonomous flight functions made it the optimal choice. Through the combination of these systems, Grey Goose is able to perform reliable autonomous takeoff, navigation, landing, and payload delivery. The ground control station consists of a laptop with external displays and the HearLink transmitter system. The laptop is loaded with Q ground control and allows for ground control of Grey Goose and any data and visualization needed as per the rules. All communication between Grey Goose and the ground flows directly to a HearLink system. The communication is then mirrored to the ground laptop via wired USB connection for the most reliable communication. Grey Goose's autopilot was initially tuned through a flight specifically designed to tune Grey Goose's PIDs by using rapid in-flight movements of different aggression levels. Throughout this tuning process, Grey Goose was flown at an empty weight without any payload. This was done due to the fact that as additional weight is added, the resulting tune only makes the drone slightly more sluggish without loss in stability during flight. Tuning at a heavier than normal weight can lead to an incorrect tune that can make the UAS attempt to correct for the weight that is not present and potentially lead to an overcorrection during flight. After being tuned, Grey Goose spent an additional 60 minutes in the air dedicated to autonomous flight testing, with no manual intervention required at any point. Over 75 waypoints were attempted, with all waypoints being reached with an average accuracy of 20 feet. Although a higher accuracy of 3 feet is achievable and will be attained during the delivery process, the waypoint navigation accuracy was tuned to be just below the 25 feet mission requirement to allow for Grey Goose to carry through speed through waypoints. This allows for increased flight range and minimizes the mission time. Obstacle avoidance, design, and testing. All obstacle avoidance will be performed visually. If any ground operator anticipates a collision risk, the GCS operator will reroute Grey Goose's autonomous flight plan to ensure minimal collision risk. In most cases, this results in Grey Goose climbing to an above-ground altitude of 400 feet and hovering until cleared to continue the mission. As per obstacle avoidance, the team has never tested its process with other aircraft posing an actual collision risk. Instead, simulated aircraft were injected into our map and the ground control station operator conducted manual avoidance through the map view. Once instructed of a collision risk, Grey Goose quickly climbed to the maximum altitude of 400 feet and hovered until cleared to continue its mission. This resulted in the avoidance of a collision throughout all flight tests. Alternatives considered. Given the performance of AAV's quadcopter at the 2023 SUAS competition, the team decided to go with another quadcopter design for the current year instead of other options such as a fixed-wing design. Along with this, the team is familiar with designing multi-rotors, meaning less time is needed to be allocated to research. Before the current airdrop system design was chosen, a similar design that involved ascending payloads by controlled resistance via servos was considered. This would have added a considerable amount of weight to the design, depleting battery life at a faster rate. The team decided against this design because a similar deployment system could be integrated while removing the weight possessed by the servos. Along with this, the servos took up additional volume underneath the base plate, limiting how close each winch could be next to one another. The team wanted to optimize the density of this entire payload delivery system to concentrate the center of gravity and limit possibilities of drag. Safety, risks, and mitigation. In order to ensure the safety of all personnel, strict guidelines were set in place prior to the development period. In order to gain access to the lab and all the tools held within it, each member was required to take an extensive training course that lasted approximately 3 hours. After completing this course, the members were briefed on the safety risks posed by the development and flight of UAVs. At all times, a safety lead was designated and kept all necessary safety equipment on hand, such as the fire extinguisher, safety glasses, lipo-safe bags, etc. To mitigate the major developmental risks, each individual component was tested before it was added to the UAV. In order to mitigate the safety risks posed by Grey Goose, all personnel are required to stand at least 15 feet away from the craft in flight. As a large multi-rotor platform, Grey Goose poses many safety risks during its autonomous flight and testing. To mitigate risks associated with the craft's proximity to others in flight, each flight always begins with a debrief to ensure all team members are aware of the craft's planned mission. At all points of the mission, a safety checklist is periodically consulted to ensure that the UAS is cleared for flight and reacts predictably during all stages. The table shown on screen outlines a subset of the specific mitigation strategies developed to minimize risks during testing and flights. In the following section, we will demonstrate how this testing has proven that Grey Goose is capable and safe enough to operate at competition. Full mission testing. 2 full mission tests were conducted with Grey Goose in competition configuration. A distance of 12 to 15 miles was used to replicate the maximal range required for waypoint navigation. Air delivery was conducted over a runway that matches the terrain depicted in the boundary area given by the competition rules. 5 objects were spread out over a similar sized area for replication of the ODCL task. Only 3 operators were used during both mission tests. Through these tests, we were able to ensure that all fail-safes and algorithms were operating as predicted. The flight personnel were also trained for efficient usage of the 15-minute setup time allotted at competition. During the 2 mission tests, total mission scores of 58.22% and 58.92% were achieved. No penalties were observed in either mission test. During the mission demonstration, we plan to score equal to our average mission test score of 58.57%. Proof of safe flight. The following flight videos cover the requirements for proof of flight piloted by Will Ponce, our safety pilot at competition. Only 1 instance of Grey Goose exists, hence only 1 instance of each required flight will be shown. First up is the manual takeoff leading to a 1,000 feet departure and a return for landing. Second is the autonomous flight from 200 feet from safety pilot, transitioning into manual mode and landing. Finally, the third shown flight will demonstrate that the drone can meet all flight performance requirements, including a takeoff and landing. These flight performance requirements consist of a 5-mile fully loaded flight, waypoint demonstration with max error of 25 feet, turn radius of 150 feet and boundary condition demonstration, angle of climb and ascent within required bounds, and an altitude check of 75 feet when 200 feet away from the runway. Summary. Throughout this season, our team worked diligently to create a fully custom UAS named Grey Goose, with the ability to perform autonomous flight, airdrop, and ODCL. Grey Goose is designed and developed around the elements of reliability and redundancy. Numerous flight simulations and tests have ensured that Grey Goose will perform well in the mission demonstration and is ready to safely participate in the 2024 SUAS competition. We look forward to competing in June and showcasing Grey Goose's capabilities.